Now what we are going to do is we are going to find out some more finite fields. We know that all ZPs are finite fields. All ZPs are finite fields. Where P is a prime. But we are trying to find more finite fields. We want to use some couple of results before we come up with some more finite fields. We need to do some more. We need to do a couple of results. The first result is, let F be a finite field. See, our idea is to start with a known finite field and construct extensions of those finite fields. Like we already did one. Z2 is a finite field, and we constructed another finite field Z2 of alpha, where alpha is the root of x square plus x plus 1. And this contains 4 elements. That means it contains 2 square elements. This 2 is a prime number. So p square elements where p is equal to 2. Can we generalize this concept? We already have a field with 4 elements. Can we have elements with 9? Well, can we have with a field with 9 elements? Can we have a field with 25 elements? So here, when we constructed the field of 4 elements, we started off with a finite element. So we are actually starting with a finite element. So this is actually a general finite field. Okay. Finite field with q elements. And E be an extension of F. And alpha belongs to E, B, algebraic over F of degree n. Then our question is, how many elements are there in F of alpha? Okay, so algebraic over F of degree n means there exists a polynomial P of x of degree n where ai belongs to F with P alpha is equal to C. Right? So how do you write the elements of F alpha? F alpha is equal to, I'm going to write it as B0 plus B1 alpha plus dash 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 Bn minus 1 alpha to the power of n minus 1, Bi belongs to F. Collection of all polynomials in alpha whose degree is less than the degree of the irreducible polynomial. What does this mean? This means that, see, each Bi's can be chosen how many times? These are all coming from F, Q times. And how many elements, how many sums are there? You know, in each element there are n such combinations. So that means f of alpha contains q to the power of n elements. Q to the power of n elements. So this is our base result. Our objective is to find out a field with p square elements, right? So what is Q here? Q is the cardinality of F, the number of elements in F. So we have to start with a field that has got p elements. This is actually of the form q to the power of n, where p is the number of elements in the base field. And that we already have, because if f is equal to zp, then this f has got p elements. Okay? Now, what is n? N is the degree of an element, an algebraic element over F. So we need to find out a polynomial like this of degree 2. This is the polynomial which makes the degree of alpha to be n. So we need to find out a polynomial like this of degree 2 that is irreducible over Zp. That is the next. So we need to establish that we need one more result. So let phi is in homomorphism from Zp to Zp, defined by phi of n is equal to n square. That implies phi of 1 is equal to 1. And phi of p minus 1, p minus 1 is an element of Cp. So it's actually p square minus 2p plus 1. Because this is, you can multiply like this, because this is a field. P square is always 0, because it's p is actually, there is no p here in Cp. The values of the elements are 0 to p minus 1. Once you reach p, and it will become 0. So there is no p square. Like that, there is no 2p. So this is also equal to 1. So phi of 1 is equal to phi of p minus 1. That means phi is not 1, 1. And that means there exists an element, let's say alpha, or not alpha, let's say A in Zp. There exists at least one element in Zp that is not a square of any element of Zp. for example, if you take C3, I am not taking P is equal to 2. I am always considering P is greater than, let's take P is greater than 2. Because for P is equal to 2, already demonstrated that there is a field that has got 4 elements. So let's take C3. 0, 1, 2. So 0 square is 0, 1 square is 1, 2 square is 4, which is 1. So this element 2 is not a square of any element in C3. That's what this says. There exists an element A. Here A in C3 is 2. So A, there is an element A in ZP that is not a square of any element of ZP. So if you consider here x square minus 2, a polynomial over Z3 of x, this will become irreducible, because if you give any values, this will not be 0. So our aim is to find out an irreducible polynomial of degree 2 in ZP of x. That is why we have this result. So that means, this actually implies x square minus a is this, which is not the square of any of the elements of ZP, is a polynomial, is an irreducible polynomial over ZP of x of degree 2. So the root of this is outside ZP, because there is no root in ZP that will make this polynomial 0. So let alpha be the 0 of x square minus a in Z2 of x, or you can just write it as so we have this condition, like F be a finite field, ZP a finite field. I'll write the same statement here. ZP is a finite field, which we already know, with the P elements and there exists an alpha in an extension field of Z2 that is algebraic over Z2 of degree 2, and that is actually x square में. This A is the element in ZP that is not a square of any element in ZP. So this implies what? This implies ZP, this is actually ZP, okay? So ZP of alpha contains q to the power of n elements. Q to the power of n elements. So here it will be p to the power of n is 2. when P is actually greater than 2. But P is equal to 2, we already saw that there is a field that contains 4 elements. We are going to conclude this session with one more result on transcendental numbers. So let us assume that there is an extension here. So let E be an extension of F and alpha belongs to E be transcendental. Over F. So that means it is outside F, somewhere here. E, F, and this is somewhere here. Because it is transcendental, it cannot be inside F. Now, let us take the simple extension of this. This is actually F of alpha. Alpha is transcendental. And we are going to take another element within F of alpha but outside F. And see what kind of element is this. Can it be a transcendental element, or can it be a algebraic element, or it has to be a transcendental element? So let beta belongs to F alpha minus F. And let us assume that beta is algebraic. Beta is algebraic. So, but the simple extension of alpha over F contains the polynomials in alpha where R of x and S of x are in F of x. Because it's transcendental, and this is how we can put the elements in a collection. Now, since B is algebraic, our assumption is B is algebraic. So B is algebraic implies there exists a polynomial P of x. Let's assume that is a0 plus a1x plus dash dash anx and belongs to F of x such that P of beta is equal to 0. That is a0 plus a1 beta plus dash dash an beta to the power of n is equal to 0. What is beta? Beta is an element in F of alpha. So it can be written like this. So this implies a0 plus a1 beta is one of this. Let's write it as r0 of alpha by s0 of alpha plus dash 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 an r0 of alpha by s0 of alpha whole to the power of n is equal to. Now what we can do is, just like we did earlier, we are going to multiply the whole equation by S0 of alpha to the power of n and regrouping the elements with alpha. So we are going to write this one as, say, polynomial in alpha. This implies, or we can say 1 can be written as B0 plus B1 alpha plus dash Bn alpha to the power of n is equal to 0. Because these are all finite elements in alphas. This implies alpha is algebraic over f, because we found a polynomial in alpha that has a value 0. This is a contradiction. Because we already assumed that alpha is transcendental and we arrived at another result of alpha is algebraic. The reason why we reached here is because we assumed that beta is algebraic. So this implies beta is transcendental. So if alpha is transcendental over f, and if you take beta outside f and inside f of alpha, that has to be transcendental. Every element in f of alpha minus f is transcendental over f if alpha is. If alpha is transcendental, every element in f of alpha minus f is also transcendental.